Testing, 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 1, 2, 3. Testing the sword and testing the pen. And by sword, I mean sound. Testing, 1, 2, 3. All right, folks, looks like it's working. So here we are with the last two sections of chapter 13, and we're going to be talking about reflexes. So let's get this chapter 3 cleaned up and done, and I can get into some chapter 14 stuff. All right, so here we go. Let's talk about some reflexes.
Any simple spinal reflex involves an afferent or sensory and efferent or motor component. The reflex is initiated at a sensory receptor. These receptors are located throughout the body. The one shown here is in the skin. Stimulation of a sensory receptor results in the transmission of an afferent impulse along the axon of a sensory neuron. These axons end in the spinal cord. In most cases, the impulse will then travel through an interneuron within the spinal cord to synapse with a motor neuron. The resulting efferent impulse travels along the axon of the motor neuron to reach the effector organ. In this case, the effector organ is skeletal muscle, and the response to the stimulus is muscle contraction. As shown, the reflex functions to rapidly withdraw a body part from a harmful stimulus. The response takes place before the brain is consciously aware of the stimulus.
All right, folks. Well, I want to point a couple of things out here on just the last part of the video. And that is right here, the purple interneuron. It said usually there's an interneuron. So usually the afferent neuron synapses with an interneuron, and then the interneuron synapses with a motor efferent neuron. When that's the case, and that usually is the case, the synapse is called polysynaptic. But there's polysynaptic. But there is monosynaptic reflexes, which mean that the afferent sensory neuron synapses directly with the efferent motor. That's possible, but most reflexes are polysynaptic. In addition, I want to point out that sometimes these reflexes don't stay in the same segment. For example, if this sensory neuron were coming in through, say, T5, at the level of the T5 spinal nerve, this interneuron could go up or down in the spinal cord, and then the motor neuron could exit at a different level, like T1 or T12. It could go up or down. And if it does change the level, it's called intersegmental reflexes. Now, sometimes the reflexes stay in the same level and they're not intersegmental, but sometimes they go up or down and leave the spinal cord at a different level in which they entered. And the last thing I want to point out is this. These reflexes happen without the brain. But you already learned pools of interneurons. So you realize that this purple interneuron here belongs to one of those neuronal pools. The information that the reflex is occurring does go to the brain, but it doesn't. But the reflex would occur even if you were brain dead. So the reflex doesn't need the brain, even if we send information to the brain about it. This is a picture showing you the same thing. It's showing you the reflex that the movie just showed you. I'll point a couple things out. This is polysynaptic. Here's your interneuron. And while you see the interneuron innervate the motor neuron right there, look at one of the collateral branches decussates. Oh, there's a word for you. Crossing over from one side to the other is called decussation. So a neuron or an axon crossing over from one side of the spinal cord to the other is called decussation. It could be from one hemisphere of the brain to the other, and that's called decussation. But a collateral branch of the interneuron decussates, then runs up to the brain. And this is where we become consciously aware that the reflex occurred. All right. I want to ask you some questions, some thought-provoking questions. If this reflex is occurring, where the hand is pushed onto a tack, the receptors detect the pain. They send a signal through the dorsal root ganglia and into the spinal cord. They innervate the interneuron, which innervates the motor neuron, and the motor neuron comes out and it innervates the biceps brachii to flex your forearm and pull your hand away from the tach. If that's the case, I want to know what must happen to the triceps brachii right here. Because if you're going to flex the biceps brachii, you better relax the triceps brachii, or the withdrawal reflex won't be as efficient. Think of the biceps brachii and the triceps brachii being contracted. You would have slower movement, if movement at all. It'd be less efficient. So I would contend that while you're telling the biceps brachii to contract, you might want to tell the triceps brachii to relax. Just food for thought. Okay, let's move on. There are different classifications of reflexes. For example, you can classify reflexes based on development. Are you born with them? If you're born with them, they're innate reflexes. Or did you learn them? And if you learn them, they're acquired reflexes. Now you might say, what the heck's an acquired reflex? Well, learning to ride a bike involves acquired reflexes. Driving a car. Haven't you ever been driving down the road and suddenly you realize you don't even remember the last 50 miles? Because you've driven down that road so much, you reflexively respond to the traffic and the conditions and stoplights and stop signs and all of this stuff. You reflexively learn that. And it's not until something abnormal appears, like a deer running out in front of you, that you respond consciously. And you might not even remember the last 50 miles of your driving because you did it all reflexively. A lot of your learned, acquired reflexes are stored in your cerebellum. And when we get to the brain, we'll talk more about that. So innate, you're born with them. Acquired, you learn them. We can classify reflexes based on the type of response. We have somatic reflexes, which are skeletal muscles, and we have visceral or autonomic reflexes, which are glands and smooth muscles and cardiac muscle. So visceral reflexes are your smooth cardiac muscles and glands, and your somatic reflexes are your skeletal muscles. The complexity of the circuit, and this is something I already mentioned. You could have monosynaptic reflexes where the afferent nerve directly innervates the efferent nerve. Or you could have polysynaptic reflexes where the afferent nerve innervates an interneuron, which then innervates the efferent nerve. So there's more than one synapse. It's polysynaptic. And the processing site. You could have spinal reflexes, which are this chapter, or you could have cranial reflexes, which is the brain and cranial nerve chapter, chapter 14. So this chapter is all about the spinal reflexes, and then we'll talk about some cranial reflexes in chapter 14. So these are classifications of reflexes. This is showing you a monosynaptic reflex. Right down here in the bottom. The stretch reflex is one of the few monosynaptic reflexes. And what happens here, without going into the great detail of the muscle spindles. I have to go into detail about a stretch reflex. But without doing that, without talking about muscle spindles, this is basically what happens. You hit the hammer on the patellar ligament and it stretches it. There is some neurons that detect the stretch right here. The neuron, well, one neuron anyway, the special structure that detects the stretch, in other words, the receptor, in other words, is the muscle spindle. The muscle spindle detects the stretch. The neuron fires, goes up through the dorsal root into the spinal cord. The afferent neuron directly innervates or synapses with the efferent neuron, and the efferent neuron comes out and tells the quadricep muscles to contract, and you kick out your foot. That's a stretch reflex, and that is monosynaptic. Most reflexes are polysynaptic. This is a withdrawal reflex. The top one is a withdrawal reflex. You went to grab the pan and the pan was hot. Receptors detected the painful heat, send it through the dorsal root, synapse with an interneuron. And now watch this. This is actually the question I posed to you. This interneuron has collaterals. one of the collateral synapses with this motor neuron, which goes down there and tells the biceps brachii to contract. All right? That's going to pull your hand away from the heat. Meanwhile, this interneuron synapses with another interneuron right here. This interneuron is inhibitory, and it inhibits this motor neuron that goes to your triceps brachii. So you're inhibiting the triceps brachii. You're causing it to relax. So you're causing the biceps brachii to contract, and you're causing the triceps brachii to relax. It makes for a better withdrawal reflex. And it only is possible because this interneuron is inhibitory and inhibits the firing of this motor neuron going to your triceps. It doesn't allow it to fire. So this is a withdrawal reflex right here. Okay, cross extensor reflex. This is kind of cool too. With the cross extensor reflex, let's say this leg stepped on a pin. All right, now what you want to do is pull this leg off the pin. You want to pull it up. All right, that's going to require contracting these quadriceps like the rectus femoris and pulling that up. But if you did that and you didn't extend your other leg, you would fall down. That's what would happen. You would fall down. All right. By the way, let me say that again because I just see that I saw something that I said something wrong. So let me start that again. I actually named the wrong muscle. Actually, I didn't for the movement, but I see what they're talking about now. You stepped on the tack. All right. This sensory neuron went up through the dorsal root, innervated an interneuron. Now that interneuron fired, and it innervated this motor neuron, and this motor neuron went down, and it told your hamstrings to contract, so you flexed your leg to get your foot off the tack. Before I talked about the rectus femoris, and yeah, that does hip flexion, but I just want to go along with the picture. So now your hamstrings are contracting, and that flexes your leg and pulls it off the tack. All right. Meanwhile, the interneuron fired to another interneuron, which inhibited the motor neuron that goes to your quads. So you inhibit your quads. Your quadriceps are your extensors. Your hamstrings are your flexors. So you excite your flexors and you flex them, and they pull the foot off the tack. You inhibit your extensors so they don't contract, which gives you a more efficient withdrawal reflex from the tack. So why isn't this just called a withdrawal reflex? This part of the reflex is just called a withdrawal reflex. But meanwhile, one of the collaterals of the interneurons decussates and comes over. And here on this side, we have crossed extension. In other words, that interneuron innervates this motor neuron, which goes down to my extensors and excites them and causes them to contract. So I straighten this leg. And meanwhile, there's an inhibitory interneuron that goes down to my flexors and inhibits it, and I relax my hamstrings in this leg. So my crossed extension is this. I'm going to contract my extensors in the leg that has to catch me from falling, and I'm going to relax my flexors in that leg that has to catch me from falling. But the leg that's being hurt, I'm going to relax my extensors such that when my flexors contract, they pull my foot away from the tack. And this is called the crossed extensor reflex. And it really is a withdrawal reflex mixed with a crossed extension to keep myself from falling. That's called the crossed extensor reflex. This is showing you the details of the stretch reflex. This muscle spindle I want to look at in greater detail, and I want to name the alpha and gamma efferents. That's what I want to name. So we'll look at this in great detail when I get the picture. But this is the stretch reflex. All right, here we go. In the muscle spindle apparatus, this is a muscle spindle apparatus right here. All right, so right here is a muscle spindle apparatus right here. When you tap your patellar ligament, this muscle spindle stretches. All right. Now, in order for this to work, this muscle spindle, which has muscle cells in it. See, there's muscle cells here. This is muscle. Plus, there's this area right here filled with the sensory neuron. In order for this to work, this muscle spindle must maintain the same tension as these quadricep muscles around it. In order for that to be true, I must have a motor neuron coming down, innervating my muscle spindle to maintain the same tension. And I do, and it's called a gamma efferent neuron. My gamma efferents innervate my muscle spindle muscles so they maintain the same tension as the surrounding quadricep muscles around it. Okay, having said that, my muscle spindles have the same tension. When I tap my patellar ligament, this muscle spindle stretches, the sensory nerve goes through the dorsal root and into the spinal cord and tells the motor neuron to fire. The motor neuron will fire and come back to the quadricep muscles. That's what it'll do. But what's that motor neuron called? Because the motor neuron that goes to my muscle spindle is called the gamma efferent. Well, this motor neuron is called the alpha efferent. So I have gamma efferent neurons going to the muscle spindles, and I have alpha efferents going to these extrafusal fibers, these fibers outside the muscle spindles. The muscles within the muscle spindles are called intrafusal fibers. The muscles outside the muscle spindle or surrounding it are called extrafusal fibers. All right. This is another picture showing you the same thing, and it's pointing out there is no interneuron. In other words, it's monosynaptic. And it's just showing the same stretch reflex we've been talking about. All right. Oh, and by the way, it points out that the alpha efferents go to the extrafusal fibers, not part of the muscle spindle, but the extrafusals. All right, that's the stretch reflex. Now, this is a Golgi tendon reflex. That's what this is. This actually keeps you from having too powerful a contraction. Let me just tell you this that you might not know. Your muscles are powerful enough to rip tendons and break bones. Okay, then how come I don't go out and pick up a load of wood and rip my tendons and break my bones? Well, here's why. When you're contracting, let's say I'm contracting my hamstrings because that's what I'm contracting in this picture. When you're contracting, there's a receptor down here in the tendon. Now the muscle contracts and pulls on the tendon. The tendon pulls on the bone and moves the bone. Simple as that. When you're contracting this muscle, it pulls on the tendon. There's a receptor in the tendon called the Golgi tendon organ. This is a Golgi tendon organ. This Golgi tendon organ, through a sensory neuron, sends a signal to the spinal cord and basically saying to the spinal cord, well, it's not saying it to the spinal cord. There's no conscious processing here. But it's sending the signal that the tendon's being stretched. That innervates an interneuron right here, and that interneuron is inhibitory. And the interneuron inhibits the motor neuron that innervates that very muscle that was contracting. In other words, it limits the amount of load that this muscle can pull on, because muscles always pull, they never push. So this Golgi tendon reflex limits the load that muscle can pull. All right. In fact, we know now that there's some drugs that override this Golgi tendon reflex. One drug that overrides the Golgi tendon reflex is PCP. And this is why people on PCP will be put in the emergency room, will be put in a dark room with no stimulus, and I mean no stimulus, no sound, no light, nothing, until they come down off their PCP. This is why people on PCP have been known to break handcuffs. And you're going to say, well, don't they break, don't they rip tendons and break bones? Yeah, they do. But they still break the handcuffs. They've been known to put their fist through a windshield. Now, I don't know if you guys know. I mean, you see it on TV all the time. It's a bunch of crap. I've seen people hit windshields with hammers, and they don't break. So putting your fist through a windshield is quite a feat. It's just as impressive as breaking handcuffs, really. So if you overrode this Golgi tendon reflex, you could generate much more power than you do. In fact, we know the percentage of power we generate compared to what's capable. A normal human being only uses about 25% of the strength for a given muscle group. That means if you're curling 40 pounds right now and you think you're doing pretty one armed. I mean, well, I shouldn't say anything that sounds too judgmental, but hopefully two arms are curling more than 40 pounds. But one arm curling 40 pounds, it's average, I guess. That's only 25% of what that biceps brachii can actually do. The reason why you're only doing 40 pounds or 50 pounds or 60 pounds is because you have a Golgi tendon reflex that limits you from doing more. Because if you did more, you might rip the tendon and break a bone. Now, PCP overrides that 20%, and you get up to approaching 100%. So you could actually quadruple your strength using PCP. You could quadruple it. Another thing that can override this Golgi tendon reflex is huge amounts of epinephrine, adrenaline. Epinephrine is adrenaline. But it has to be a massive release of adrenaline or epinephrine. It can't be just, the dog barking in the alleyway makes the hair on your neck go up. It can't be that amount. It has to be this huge release. But you've probably heard of stories of a mom lifting a car off her baby or stopping a car from rolling down a hill or something like that for her baby. Well, that is because the massive release of epinephrine overrode her Golgi tendon reflexes. Now, did she rupture tendons and tear them and rip them and potentially break a bone? Yeah, probably she did. But she didn't care because she's just trying to get the car off the baby. So she overrode that and was able to do, Herculean efforts and strength of movement. So that's the Golgi tendon reflex, where you actually inhibit the muscle contraction. We already did the withdrawal reflex. This is adding the reciprocal inhibition. The extensors are inhibited. So with the primary withdrawal reflex, when the interneuron fires and stimulates the biceps brachii, an inhibitory interneuron right here is going to fire and inhibit this motor neuron for the extensors. And that makes for a more efficient withdrawal reflex. This is also showing you the withdrawal reflex. In this case, no, it's not showing you. It's showing you the withdrawal reflex, but it's not showing you the reciprocal inhibition. It's not. It's just showing you the hamstrings withdrawing from the tack. That's all it's showing you. So we already looked at this. But this is showing you the hamstrings withdrawing from the tack and the quadriceps being inhibited because they're extensors. And of course, and the other leg with the crossed extensor reflex, the opposite's going to occur, and this keeps you from falling down. When you pull one foot off the tack, what keeps you from falling down is your other leg. Let's say you're pulling your right leg off the tack. So in your right leg, you inhibit your quads and you excite your hamstrings. But in your other leg, you're going to inhibit your hamstrings and excite your quads so you stay standing. And that's the crossed extensor. And this is the crossed extensor. So this is the second or third picture of the crossed extensor we've looked at. So as you can see, these reflexes get quite complex as we keep adding to them. Remind me in lab next week to show you a crossed extensor reflex. If you remind me to show you a crossed extensor reflex, it won't be with the leg, it'll be with the arms, but I'll show it to you and it should work for us. I'll show you one. This is crossed extensor again. So it's beating you up with the crossed extensor reflex. All right, this is just saying that no, you don't need the brain for these reflexes to work. However, you use the brain. These interneurons decussate and they ascend to the brain. And can the brain modify these? Yeah, the brain can modify these. The brain sends descending tracks down. For example, and I think the book had this example. I read it someplace anyway. If you were walking a tightrope across the Grand Canyon and a bee stung you, you would override your reflexive movement to slap that bee, kill it, or maybe jerk away from it, or whatever. And why would you override that reflex? Because you're walking a tightrope across the Grand Canyon. Your brain makes the decision that you would rather tolerate the bee sting and not fall off the rope than reflexively react and fall off the rope. So yeah, you can modify these reflexes. Your brain can override the reflex. And of course, you can see this descending information from the brain that can modify this reflex, of course. So there you go. All right, so this is showing you 5 general characteristics of polysynaptic reflexes. First of all, they always involve pools of interneurons. That's the definition of polysynaptic. The afferent doesn't directly innervate the efferent, it goes through an interneuron. They are usually intersegmental in distribution. And what that means is this. Let me go back. Intersegmental in distribution means that these interneurons go up or down the spinal cord before, like this interneuron right here, can go up or down the spinal cord before innervating that motor neuron. Of course, this interneuron is going up the spinal cord because it's going to the brain. So these polysynaptic reflexes are usually intersegmental, but they don't have to be. These polysynaptic reflexes involve reciprocal inhibition. What reciprocal inhibition is when you tell your biceps brachii to contract, you tell your triceps brachii to relax. When you tell your quadriceps to contract, you tell your hamstrings to relax. When you tell your hamstrings to contract, you tell your quadriceps to relax. And these polysynaptic reflexes usually have reverberating interneuronal pools. Now remember what the reverberating circuit was. Here's a neuron firing on that neuron. Okay. Meanwhile, a collateral axon comes up and innervates the first neuron that fired that made this fire faster. This is a reverberating circuit. So neuron number 1 fires, and it innervates neuron number 2, which innervates neuron number 3. And what happens is a collateral axon in here branches and goes back and facilitates neuron number 1, which makes it fire more efficiently, which makes neuron number 2 fire more often, which goes on and makes neuron number 3 fire more often. Meanwhile, a collateral branch goes back and facilitates neuron number 1, which makes it fire even faster. So this is a reverberating positive feedback circuit. And what this does is this prolongs the reflex. It's a positive feedback reverberating circuit. And it prolongs the reflexive motor response. So that's what this reverberating circuit does. And quite often, with these polysynaptics, several reflexes cooperate. And if you look at the crossed extensor reflex, that's actually a mixture of several reflexes. That's actually what crossed extensor with reciprocal inhibition. Now that's a complicated reflex. Reciprocal inhibition. Go back and look at crossed extensor reflex with reciprocal inhibition, and you'll see several reflexes are coordinated really. All right, so that's the characteristics. That's some general characteristics of polysynaptic reflexes. Lastly, we have some reflexes. Well, doctors check lots of reflexes. They're checking for spinal cord damage. The cranial reflexes we'll talk about, they're checking for cranial nerve damage. There's 12 cranial nerves they're checking. So in this particular reflex, it's a famous reflex called the Babinski reflex. What happens is if you are a normal adult with normal descending motor pathways and you rub the bottom of the sole, the lateral sole of the foot, the sole means the bottom, that was redundant, the lateral sole of the foot, what will happen is your toes will curl. And that's a normal Babinski reflex or a negative Babinski. It's a negative Babinski. That's supposed to happen in an adult. Now, in a child, before they have properly developed descending motor tracts, when you do the Babinski on them, their toes flail or flare. Flail or flare. And this is a positive Babinski. Now that's negative or that's negative. That's normal in a child. A positive Babinski is normal in a child. All right. It just means that they don't have properly developed descending inhibition. That's all it means. And it's not a bad thing in a child. But if you do this to an adult and their toes flail, that's pathological. If they have a positive Babinski, that means there's some spinal cord damage. So doctors will do this Babinski reflex to check for spinal cord damage.